Good morning, students. Welcome to today's lecture. Is about flat pulley derivation. So we are going to derive the equations that are responsible for flat pulleys, and we will consider a flat belt passing around a flat pulley so that the angle of lap is designated as theta and the tension in the belt are T1 and T2. When it is just on the point of slipping, let's examine all a small element of the belt. So here we consider an infinite small region of the belt and look at the forces that act on it. So the flat pulley drive radial equilibrium is as shown in this figure here, where T1 is the tension at the slacken end and T2 is the tension at the tighter end. So we know that the pulley has the slacken and the tighter end. Then now to derive the equation, then we will consider the point of contact. If this is the radius of the pulley and T being the tension and T2 also being another tension. So if we consider the elemental region as shown here by the shaded region in green, in green, and the radius as r, and the angle between those points is theta, then the point where it makes the contact, if we draw two normal forces, one which is parallel and another one which is perpendicular to the point of contact, then it is true that we can resolve the tensions into two components, the horizontal component and the vertical component. So that will give us the reaction force in the horizontal as well as the friction force, and we know that the friction is calculated by the coefficient of the viscous drag times the normal force, and the normal force here is N. Therefore it is true that on the angle that of the region of contact of the belt is theta, then when we resolve the normal of the tension T1 and T2, the angle between the tension belt and its horizontal line is half the angle of contact of the belt. So that is delta theta divided by 2. So then if we want the sum of the vertical forces, then we will take the tension T times the sine of the angle delta theta over 2, then plus that is for the T side, and for T1 side we know that T, because this is the tighter end, we'll have T plus delta T, then sine of delta theta over 2, that should be equal to the vertical force, which is the normal N. They should be the sum of vertical forces, opposite forces, they sum up to 0, so N is equal to that. So then it is also true that if we simplify this and we remove the brackets of the T by multiplying delta theta over 2 with the T and delta T, then we will get an equation whereby 2T delta theta over 2 plus delta T delta theta over 2 is equal to normal. So then we can conclude that the product of this is so small that we can neglect it. Therefore the tension T times the small angle delta theta should give us the normal reaction N. So then how do we get the tangential equilibrium? The tangential equilibrium is obtained by looking at the cosine of the two forces components. Remember, we have tension T1 and tension T2. Therefore for T1 we have T cosine delta theta over 2 plus the coefficient of the friction which is the force due to friction drag, which is nu times n. This is equal to T plus delta T cosine of delta theta over 2. So if delta theta is very small, then the cosine of delta theta will be equal to 1. So therefore we can conclude that the frictional force is equal to the increment in the tension, the delta T. So then flat belt drive, we already saw from radial equilibrium that the tension times the small angle change is equal to the reaction force, and therefore equating the frictional force with a small change in tension, then solving, we'll get that the coefficient, the integral from 0 to angle theta of the friction, coefficient of friction times the small change in angle should be equal to the tensions, the two tensions, the difference in the two tensions T1 and T2, and small change in tension divided by the overall tension. So students, these are the most important equations for the flat belt drive. Let's again meet in the next class for other types of equations